Yeah, that's my good buddy from Atlanta, Georgia, Jeff Crompton on the saxophone. Jeff is in a lot of jazz and blues bands. He's the most talented guy I know, perhaps the funniest too. That's from an album with his with a band called Scott Hooker and Friends, and the album's name is, believe it or not, Standard Deviation. The song, In Another World. I know you think I'm in another world, but my friend Jeff is in a whole nother world. All right? There's his website right there. If you're interested in his music, you can go check him out yourself. Jeff Crompton, the incomparable Jeff Crompton, plays saxophone, piano, and lots of other instruments that he's good at but doesn't admit. All right, so moving on. This is part two of a presentation about measures of variability. All right, so in the previous episode, we took a look at this way of thinking about things. We covered measures of central tendency, which tells us about the middle of the tent, tells us about the middle of a data set. And of course, we're interested in how spread the data is too. And so measures of variability tell you how wide the tent is, all right? So we already covered the range and the interquartile range, and we left off at this point. We saw the limitations of the range and certainly the interquartile range, and we wanted a single number, like the mean. Okay, the mean is a single number that tells us about the middle. We'd like a single number to represent the spread that's not so sensitive to the extreme scores like the range is. And so what I'm looking for in this presentation is an average amount that the scores differ from the average, okay? So you're all familiar with the average, with the mean, okay? You learned that back when you were a little kid, okay? But not many of us learn about this other measure, which is another kind of mean, if you will. That's the point I'm going to make in this presentation. We're looking for another kind of mean, the mean amount, the average amount that the scores differ from the mean, okay? So everybody differs from the middle of a distribution by some amount. We'll collect all those, add them up, and see if we can get an average of sorts, okay? So let's walk through this with an example, all right? So instead of looking at numbers of participants, let's look at one participant and sample how much beer he consumes in a week, okay? So here's my x, my variable is the number of beers consumed each day, okay? So on the first, I'm not going to say who this is, all right? So on the first day of the week, Monday he drank 1 beer, on Tuesday he drank 2, and so on Wednesday through Saturday, all right? So there's Monday through Saturday. Fortunately for his liver, he takes Sundays off. Okay, well, to begin getting a measure of how much the scores differ from the mean, we got to go get the mean, all right? Now, you already know how to do the means, but bear with me. This is a tutorial. I'm posting this on the course page, this PowerPoint presentation, and I want you to go through it as many times as you need to until this sinks in and makes good sense to you, okay? So as you're about to see, this is a very helpful step-by-step tutorial that I've made for you, all right? So I don't skip any steps, one click at a time. So here we go. We're going to get the mean first, all right? To get the mean, we simply add up all of the x's, add up all of the scores, okay? And so those add up to 30. Now, by the way, what you should be doing right now is following along just as if you were in class. And in class, I would have everybody have their calculator out, and I would say, hey, be punching along and calculating everything just along with me here, okay? For all my presentations that are to follow, where we're starting to go through numbers and crunch data, don't just sit passively and watch this, okay? Have your calculator out and do it step by step with me. It's like learning how to ride a bike. You can watch me teach you how to ride a bicycle, but you all remember once you got on that bike, it was a little wobbly. It was like, wow, that looked easy. I watched my brothers and sisters do it, and I watched whoever's teaching me how to ride the bike do it. I'm going to tell you how to ride the bike. I'm going to demonstrate how to ride the bike, but you need to get on the bike and tip over a few times. So you need to do these examples. So follow along with me. Take notes as if you would in class, and then go through those notes. Go through the calculations step by step yourself so that you know how to do it. So on exam days, you're not riding the bike for the first time, wobbling or tipping over. You don't have time to wobble and tip over on exams. So do it step by step. Pause now and get your calculator out. Verify that this adds up to 30, okay? I'll wait here. Okay, you're back with a calculator. Here we go. All right, so these scores add up to 30. He drank 30 beers in a week. You can discuss whether you think that's a rational amount of beer to drink in a week or not. All right, N is not the number of people for this example, but the number of data points in my sample. Okay, we're sampling one person, and okay, so there's 6 days of the week, so that's what N is, six numbers of beers. Okay, so you know how to calculate the mean already, but again, there's your official formula for it. This is a sample, so I'm calling it X bar, and so we added up the scores and plug everything in, and so 30 divided by 6 equals 5. Now, trick question. Well, not a trick question at all. What's wrong with that answer? That answer's not correct. What's wrong with that answer? Think about it. Pause. Pause if you have to. Okay? And think about what's wrong about that answer. Why would I only give you partial credit for that answer? 30 divided by 6 is 5, is it not? Is it not? Well, what should I have done? So I've got a mistake on here in my own presentation. Don't do what I do, all right? I said our rule of thumb is to round things to 2 decimal places and display final answers to 2 decimal places. And the official rule was when you start with whole numbers, do it to 2 decimal places beyond what you start with, okay? So we start with whole numbers, so my final answer should be 5.00. I would only give you partial credit for that. Okay, to me there's a difference between the number 5 and the number 5.00. 5.00 tells the reader, hey, to 2 decimal places, to the 100th decimal place of precision, the answer is 5. Okay, when it's just 5 without any decimal places, the reader's left wondering, well, gee, was it 4 point something or 5 point something rounded down or up to 5? Okay, so do what I say, not as I do. That should say 5.00 on the screen. Okay, so anyway, the mean is 5. 5 beers per day is the average amount that Homer drinks per day. Okay, now what's wrong with that number? Other than what I just said, what's wrong with that answer? Look at the raw data. Okay, one thing that's wrong with that, it's not really wrong, but one thing that happens sometimes with the mean is the mean sometimes is a number that's not even reflected in the data set. Okay, so there isn't a day of the week that he actually drank 5. He always drank less than or more than 5, but it averaged to 5. Okay, so that's one little tiny problem that we have with the mean sometimes. It might not actually be a member of, we're saying our best guess for what Homer drinks per day. If you had to guess and you couldn't see the answers, your best guess would be 5. Okay, and every time you're guessing for every day, you shouldn't be wandering your guess around and think, well, I think he drank 2 today and 10 this day, and you should just stick with the mean if you know it. The mean is always going to be your best guess. It's the score around which there's the least amount of deviation. Okay, so in the long run, that's the least amount of deviation. That's the best guess. You should guess it every single time. Okay, even though he never had 5 beers in a given day. All right? Okay. Maybe another thing wrong with 5 beers per day is it's kind of a lot of beers per day. All right, but Homer is Homer. Okay, so we have our measure of central tendency, and for a good interval ratio, well, this is a ratio scale variable, number of beers consumed. This doesn't seem to be skewed in any kind of noticeable way, so the best measure is the mean rather than the mode or the median. Okay, so we have our measure of central tendency of choice here. Now let's get a measure of variability. Now the range, once again real quickly, is the high score minus the low. 9 is the most frequent number of beers, minus 1 is the fewest. 9 minus 1 is obviously 8. The range would be 8. We have a range of 8 beers. Okay? But we don't like the range. Okay? We don't use it all that often, but there it is. So, once again, to remind you of the goal here, the goal is to work our way to an average. Another average. There's an average 5. Now I would like to know the average amount that he differed from 5. Okay? By how much did he differ from 5 on average? Some days he drank less, some days he drank more. If there was a day that he drank 5, he didn't differ by any from 5, but every day you differ by some amount, even 0 is an amount. So we want to get an average. What's the average amount of that deviation? Okay, so the first step is to get those deviations. Okay, so I'm going to create a column in my sheet here called x, little x. Okay, you can see next to the big, it's a little x. Okay, not to be confused with the raw x, the big scores, the raw scores. Okay, so let's get a column of little x's. All right, just to remind you, little x is each score minus that. Whoa, got ahead of myself. Sorry. Is each score minus its mean. So I don't need this column here, but just to make it really, really obvious for this tutorial, I've plugged the mean in as a column. So to get little x, it's 1 minus 5, 2 minus 5, 3 minus 5, and so on. Okay, so my little x's, here they come. There, I now have what are called deviation scores. So on Monday, Homer drank 4 less beers than average. On Wednesday, he drank 2 less beers than average. On Friday, he drank 3 more beers than average, and so on. Okay, so some days he drank less, some days he drank more than average. Okay, so there's the raw number, not the raw number, yes, there's the raw number of deviations, okay, the deviation scores. All right, so are you with me? I want to get the average of these deviations now. So here's my formula for getting what we call the mean deviation. So now I'm going to have little x bar, just like to be consistent with big X bar for a sample mean, the raw mean. Now I'm going to get the mean of the deviations. We'll call it the mean deviation, all right? So little x bar. And to follow this, a mean is a mean, right? You add up something and you divide by the number. So now we're going to add up the little x's, not the big x's, and divide by n again. So get your calculator, if you need it, and add up these 6 numbers. What does little x equal? All right? Well, if you did it like me, that adds up to 0. All right? That's interesting that they would add up to 0, but we have a mission. Let's proceed. All right? So the sum of little x, the sum of the deviations is 0. They have added up to 0. So let's plug it into our formula. So 0 goes on top, n is still 6. 0 divided by 6, well, 0 divided by anything is always going to be 0, all right? So since the deviations added up to 0 this time, the mean deviation turns out to be 0. So, the mean deviation is 0. He differed by 0 from the mean. Well, as I said, 0 divided by anything always equals 0. And this seemed like a good idea at the time. And this isn't just a quirk of this data set, okay? It wasn't just this funny example that I came up with that happened to add up to 0. If we do this, it will always add up to 0, okay? The only time it won't add up to true 0 is if you had a quirky mean that you had to round, okay? When you did that first division for the mean, if you rounded your mean, then your deviations might not add up to 0. It'll be within what we call rounding error of 0, okay? So it's going to be 0 or within just a tiny bit from 0, okay? You know, a 1 or 2 hundredths probably, typically, away from 0, okay? So when you do this step by step, if you get a number different than 0, or you know, if you had to round greatly different than 0, you must have made a mistake, and everything else we're about to do will be wrong. So this, you don't have to do it my way, but I'm going to teach you this way of filling out this table, and I encourage you to use that for this course, okay? And do this step, add them up. Don't just assume they'll add up to 0. Do that. Make sure that they add up to 0, because if you made a mistake here, the rest will be wrong. So it's a good check along the way. Okay, so nuts to that. It seemed like a good plan. And the mean deviation of being equal to 0 is not it's not wrong. We didn't do anything wrong here, right? It will always be 0. The mean deviation will always be 0. And that's basically defining the mean, okay? A few presentations ago, I gave you this definition of the mean. It was a very unsatisfying definition, okay? The mode, the median, they're easy to define. When you get to the mean, it's kind of hard to define it without just telling people how you got it. Well, you add them up and you divide by the number, okay? The mean is the score around which we have the least amount of variation, okay? You don't have less than a total of 0. I mean, there's nothing, there's no less variation than 0, okay? So it's just kind of proving the definition of the mean, okay? But it seemed like a good idea. It seemed like a good idea. And if you were following along, you probably agreed with me. It's like, hey, let's get a mean amount that they differ. Well, the mean amount that they differ will always be 0. But look, there's numbers there, okay? It's just those pesky plus and minus signs that screwed us up, okay? So kind of like a Scooby Doo episode. If it wasn't for the pesky, plus and minus signs, we would have gotten away with this strategy. If only there was a way that I could get rid of them. If only I could get rid of those pesky plus and minus signs and just concentrate on the numbers, I'd have a goal. All right? What can we do to get rid of plus and minus signs? Let's think. I'm absolutely stuck. This is an absolute dilemma. I'm going to need a shot of absolute vodka soon if someone doesn't help me out, okay? All right, so in class, this is where I'm waiting for people to give me a suggestion, all right? Somebody says, take the absolute value of each deviation. That's interesting. Sounds like an absolutely terrific idea. Ha, ha, ha. Let's try it out. Okay, so when you put a number in those brackets like that, that's pretty universal symbolage. Is that a word, symbolage? For taking the absolute of a number, all right? So an absolute number is just ignoring the signs. You just strip off the signs, okay? So here they are. And again, just to fully remind you what this column is, it was each score minus its mean, taking the absolute value. So we just get rid of the plus and minus signs. So -4 becomes 4 and +3 becomes 3, okay? So there they are. Now that's just raw numbers, okay? So I'm back on track. Let's proceed with this attempt to get an average of some sort, okay? So I'm going to add those up so I can plug them into a formula I'm about to show you. So now I'll call it the sum of absolute little x, sum of the absolute deviations. So I add those up, and so do you with your calculator, right? Do that, pause, verify that this adds up to 18. And I want a new, so I've got the mean deviation fell apart because of the plus and minus signs, but the logic was good and strong. I liked my logic. So I'm going to proceed, and I'm going to now calculate something that I call the mean absolute deviation, or the MAD for short. This is my own creation, okay? I didn't create this. I created the name. I'm proud of it, all right? Other people, your book, I think, if I remember right, your book calls this, what I'm about to do, the mean deviation. And if I'm correct in accusing your book of doing that, it's wrong. This is the mean deviation, what we just did. Others call this an average deviation or the absolute average deviation. Other books, other authors use different terms. I got my own. I got mad that the first thing didn't work, so I created the MAD, the mean absolute deviation. All right, what's it going to be? Okay, the absolute little x bar is what we call this symbol here. And just as I've been doing, you add something up and divide by n. So again, I added up those raw absolute deviations, plug them in, 18 divided by 6, and it's still 6. 18 divided by 6 is 3, and again, I should say 3.00. Don't do as I do, do as I say. So my MAD is 3.00. Voila! We have the MAD. Let's talk about what this MAD means now, okay? Don't get lost in the forest here. Don't forget the big picture here. All right, what does this number mean? Let's back it up and refer it to the mean of 5. So right now what we're saying is Homer drinks 5 beers on average per day. Some days more, some days less, okay? And on average, he deviates from 5 beers by 3 beers. On average, he deviates from 5 beers by 3 beers. I should be technical and say by an absolute mean of 3 beers. Let's take a look at the raw numbers again. So on day 1, he had 1 beer. He deviated by 4 that day, okay? So it was, 3 is not far from 4. On the second day, 3 was smack dab on. This MAD equals Tuesday's consumption, how it differed. One off on the next day, one off on the next day. On Friday, it's smack dab exact, and one more on Saturday, okay? So it's a pretty good measure. It's a pretty good guess of the amount that he differs from the mean. So there we go. We should be able to go home now and be done. We have a single number representing the average amount that he differs from average. All right, the mean amount that he differs from the mean. We should be done. Okay. Well, sadly, we don't use that. I walked you down a little dead end here. Okay. The MAD is never called the MAD, but whatever people call it, it's never used. This strategy is rarely, if ever, and I will go so far as to say never reported. Okay, you'll never read a journal article where they've computed this and reported it. Okay, so it's wonderful. It worked. You saw it in action. It should be what we use. Okay, but we don't. For reasons that are over my head, we just don't use it. So I'm sorry for walking you through that little that was a little dead end in our maze here. So we need to backtrack and come back to our goal. Our goal hasn't changed. I would like some kind of average amount that the scores differ from average, but doing it by absoluting, if that's a word. We absoluted the numbers, and it worked, as we just saw, and created the MAD, but the MAD just ain't used. Okay? So I'm back to the pesky plus and minus signs. What can I do to get rid of them? I still need a suggestion. So, can you think of anything I can do to get rid of plus and minus signs? What can you do? Don't be a bunch of squares. Come on. All right. Oh, square the numbers, okay? What an excellent idea. What if we took this, what if we squared each one of those little deviations, all right? Because when you square any number, it becomes positive, okay? Positive ones remain positive, negative ones become positive, all right? So, excellent idea. We'll square the little deviations. This is a good time to point out these are not squaring the raw scores. This is not a big X squared. Lots and lots of students in this column make this mistake. Don't make this mistake. I'm not going back and squaring the raw numbers. I'm squaring the absolute numbers, or, well, these technically I'm squaring the raw deviations. Okay? So, they are coming from this column, not from the first big X column. Okay? So negative 4 squared is 16. Now let me just give you a tip when you're doing this by hand with your calculator. Don't waste all of your time punching in those negatives and positives, okay? Just put 4 squared, whether it's a negative 4 or a positive 4, okay? Because the squaring doesn't matter. It's going to become positive, okay? Now another mistake I see some students do in this column here is we're squaring the numbers, okay? A number squared, if you don't have a square button on your calculator, is you multiply the number by itself, okay? 4 squared is 4 times 4, not 4 times 2. I'll see students multiply a number by 2, thinking that's squaring, okay? Don't make that mistake, okay? Don't grab the wrong numbers, and don't just multiply the right numbers by 2. You multiply them by themselves. 4 times 4 is 16. 3 times 3 is 9. Okay, so I now have a column of squared deviation scores. Let's continue on my theme here. I'm going to add those things up. So now I'm going to sum I'm going to call this sum of the squared deviations. Okay, sum of the squared deviations. All right, so add those up. Grab your calculator, add them up. Adds up to 68, right? You're calculating it with your calculator, aren't you? Adds up to 68, right? You're not getting 68? Interesting. Try it again. When you're doing something and it doesn't agree with what you see others in a class doing or what you see the teacher doing up in the front, you double check your work, all right? You double check and it still doesn't add up to 68. All right, might want to check my math, okay? So you've done all this, you calculated it, haven't you? Well, the moral of this little story is don't ever trust me. Trust me, don't ever trust me, okay? Just because I got a slick PowerPoint doesn't mean I'm infallible, all right? Sometimes I'll make mistakes on purpose. I do this in class to make sure people are paying attention. And whenever I do make an actual mistake, I can then claim to have made it on purpose. See how that works? So sometimes mistakes are made, whether they're purposeful or not, and you should never trust. So the rule when I'm in a class is that the person up at the board in the front doesn't have to have a calculator and do the work. There's a room full of people with calculators, and you're all at home with calculators. Your job is to add things up and do the math, not the presenter. So you should be always double checking. Okay, so by now you figured this out. I was wrong. They don't add up to 68, they add up to 58. Double check your work. Nobody likes doing work by hand, especially these days, okay? So, but can you see how any little mistake along the way is going to snowball and everything else will be wrong? You know, if you didn't get the mean right, everything was going to be wrong. If you didn't add something up, your final answers were going to be wrong. If you didn't square something right, even just one number, if you got, if you put something wrong here for any one of these, that total's wrong, the rest of the answers are going to be wrong. It's very frustrating, but you can prevent that by double doing your work, okay? We'll always use small examples like this, and I know it's tedious, but hey, we're not doing 1,000 numbers. You can redo 5 or 10 of them, okay? So always double do your work, especially on exams and homework, okay? Do it twice, because if you get 2 different answers, you do it a 3rd time, and the one that turns up twice is probably the correct answer. Okay, so let's proceed. I've added those things up, and now they correctly add up to 58. I need a name for what I'm doing here. So I hated the mean deviation, okay? It fell apart. I loved my logic. So that made me mad, and I created the mad. And then the mad got rejected by the world, and that made me sad. And so I came up with another new thing, okay? So I'm going to calculate what I'm going to call, this is my own personal creation again, I'm going to call this the Squared Average Deviation, okay? The SAD, all right? All right, it's time to quit playing fantasy, okay? I don't get to name things. I should be able to get, I could have done better than a lot of the things that we're going to see in this course, okay? So, I like the SAD. I like the Squared Average Deviation. It tells you what it is, okay? But the gods that be decided that we're going to call what I'm about to calculate the variance. The variance. Flippity-doo. The variance. All right, what the hell is a variance? Squared average deviation of the SAD. That's catchy. It tells you what it is. What does the variance tell you? Nothing. All right, so as you can see, I'm still bitter. I'm back to being mad about this. All right, so I got to call it this. I got to call it the variance. Okay. The variance now is going to have 2 symbols, whether we're referring to a sample or a population. Maybe you recall when we're doing population parameters. If the data we're jerking with is a population, we use Greek symbols. And this is the lowercase Greek sigma, not to be confused with this uppercase Greek sigma up here. Okay? Yeah, I know stats can be wonderfully fun and confusing. All right? So big sigma means to add something, and little sigma means the variance. Well, sigma squared is the variance. S squared is going to be equal to the variance. Okay, so if it's a sample, which I'm doing here, we should call it S squared. If this was population data, what I'm about to do will be called sigma squared. Now the formula, with the thing creating this is exactly the same in both cases, and it's just what we've been doing here. When we started with the mean, we added up, divided by the number of numbers. We added something up, divided by the number of numbers. We added something up and divided by the number of numbers. And here for the variance, we're going to add something up, the squared deviations, and divide by the number of them. So let's plug in our numbers that we know. We added that up to 58, and it's still 6. 58 divided by 6 is 9.6666 forever. I said to round things to 2 decimal places, so I'm finally doing things right. And the answer for the variance is 9.67. Boom, we got the variance, all right? Now, what does that mean? That's not a very satisfying number because, again, our goal was to figure out the average amount that Homer differed from 5. The average amount that he differed from his average. Okay? Well, this is suggesting that he differed by 9.67 beers from the average. Well, that's terrible because that's more than he ever drank. We're saying that he differed by an amount that's more than he ever even drank. On his most, on Saturday he drank only nine beers, okay? And we're suggesting that on every day he differs from 5 by about 9 2/3. See, the variance sucks, all right? So it's correct. What we just did is correct. The variance sucks. What sucks about it? Why is it such a screwed up number? Well, it's distorted because we did all that squaring up here, okay? So we squared the numbers out of the ballpark, all right? So what can we do to fix this distortion? And this is where I get mad again, because we didn't have to do nothing when we calculated the MAD. Boom, we were done. We had a nice number, 3. Boom. Now we got to do some adjusting. We had to do some freaky squaring, and now we got to do some freaky unsquaring, okay? So we'll have to unsquare our answers. I don't know. I like to make up words. We're going to unsquare our answers. Okay. I guess that's not a word. We got a better word for that. In math, we call it the square root. Okay. So if we get the square root of the variance, we'll have a number that's back down at least in the ballpark. So let's do that. Well, when we do that, we're creating and calculating our final answer here. Okay, so the variance by itself, 9.67, is not, it's a descriptive stat. Don't get me wrong, we did it correctly and the variance is a right number. But it's no good as a descriptive stat because it doesn't really describe what's going on here. The numbers were squared. So when we do this unsquaring thing, we are going to wind up with what we will now call the standard deviation. Okay? Artistically covered by my friend Jeff Crompton at the beginning of the video. Standard deviation. Okay, did you know there's a soundtrack to the Standard Deviation? Now you do. It has its own album. Okay. All right. You can pick it up at a record store somewhere on earth, I'm sure. Find Scott Hooker and Friends album, Standard Deviation. Okay. Well, again, whether we're doing it for a sample or a population, we'll have the correct symbol down here. So we're doing it for a sample here. So I'm going to take the square root of whatever that variance was, okay? The square root of s squared. S squared is the variance. Take the square root of the variance. If it was population parameter, up here I would have been calling it sigma squared, and I would take the square root of sigma squared. See, these are mathematically the same thing, just two different symbols to tell the reader which type of data set you're working with. Okay, so let's do it. The square root of 9.67 is, you do it yourself. What's the square root of 9.67? And you should get a number that you would round to about 3.11. Okay? So 3.11. There, we're done. We have the standard deviation. Now, I'm going to sound a little bitter still. I still like my MAD. It was easier. I like that it was a whole number in this for this example. Okay? Look what we got here. We got a little artifact. We got 3.11. What this is suggesting is that Homer drank 5 beers on average, and he differed from 5 by an average of 3.11 beers. On average, he drank 3.11 beers different than the mean. And the 0.11 is what I got a little problem with. That's a little artifact kind of caused by all this squaring and unsquaring. And it comes to point with this example here, okay? On no particular day did Homer ever fail to finish a beer. That's on, Homer doesn't fail to finish a beer. He didn't drink 2.5 beers, or, he never drinks 3.11 beers, okay? So that's one thing I don't like about the standard deviation is you get a little bit of artifact sometimes, okay? So it's not as clean. It's a similar number just to the MAD, but it's not as clean, okay? So now I don't want you to get too lost here. So I hope you followed my logic here, okay? Every step along the way, I've been saying how I want to get a single number that is another kind of mean. So the standard deviation is kind of a mean. And I'm always going to say kind of or sort of, or if I want to be technical, I'll call it's an index of the average amount. Okay, so when I say kind of, sort of, it's an index. It represents, that's either sloppy or technical ways to just sort of say that there was some squaring and unsquaring, so it's not exactly the average amount. It's representing the average amount. It represents the average amount that the scores differ from the mean. Okay, so 5 beers is the post in the middle of Homer's beer tent. Okay, and sometimes he drinks more than 5, and sometimes he drinks less than 5 beers. On average, sort of on average, he differed from that tent post in the middle of 5 beers by about 3.11 beers. Okay? He differed from the tent post in the middle by about 3.11 beers. That's all the standard deviation is. It's kind of another mean. People get all freaked out and mystified by it. That's all it is. And I hope you saw that logic every step of the way here. It represents the average amount that the scores differ from the mean. Okay, not to confuse you, but here's one more thing you can say of what a standard deviation represents. You'll sometimes hear it described this way. So I've always been referring to the middle of the tent here. So that was to be consistent. But here's another way I can refer to the standard deviation. It's not just how much the scores differ from the mean, it also winds up being, it's the mean amount that the scores differ from each other. Okay? The mean amount that each score differs from the other scores. Okay? So technically take any two values, and 3.11 is about the average amount of difference that you see between any two of the scores. So it's the average amount that the scores differ from the mean, and the average amount that the scores differ from each other in a data set. Whether that's a sample, which we have in this example, or if it's a population. Okay? If these were the only 6 days of beer drinking that Homer ever did, it would be his population of beer drinking. Okay? But no, it's just 1 week in his life. So it's a sample. Okay? So, let's just recap what we've covered in these last 2 presentations here. So we covered measures of variability, and I introduced the range, the highest score minus the lowest score. I just mentioned the interquartile range. We're never going to use it again in this class. And you shave off the upper 25% of the scores and the bottom 25% of the scores. And so technically it's the 75th percentile score minus the 25th percentile score. So it's that middle half that remains. Okay, that's all. We'll never see that again in this class. Then we walked through what we did today, and we went through the mean absolute deviation, the MAD. That was a dead end. Then we calculated the variance. Okay, we're going to tuck the variance into our utility belts, and we're going to pull it out at the end of the semester. Okay, this course ends with coverage of what's called the analysis of variance, sometimes called the F test or the ANOVA. That's where we're going to end, covering something called the analysis of variance. So variance will kind of rear its ugly head back then. Okay, it's a descriptive statistic, but it's not a good one because it's been squared. So then we unsquare it by taking the square root sign, taking the square root of the variance, and we call that the standard deviation. Okay, the standard deviation. So in the next presentation, I'm going to yuck this up just a little bit, and we'll save that for next time. So what I would strongly recommend you do is perhaps review this whole presentation. If nothing else, or perhaps in addition, take a look and walk through the PowerPoint itself. I've placed the PowerPoint up on the course page, and you can go like I did, step by step, and see every step, and you can go back and you can go forward. I'm really proud of that tutorial. It's just that. It's a tutorial kind of presentation, okay? So make sure you go through it, whether watching this again or doing it yourself, or both, okay? Try it out. Have your calculator. Make sure you know how to do it. So that's what we're going to be doing. We'll have some examples that we'll be doing. I'll give you some examples, some homework kind of examples, and you'll do them from scratch. But make sure you can do this one, okay? I've showed you how to ride the bike. You watched me. I told you all about the theory of riding a bicycle. I've shown you how to ride a bicycle. You must get on the bicycle and practice it. It's not enough to just watch and assume that you'll know how to do it. Your fingers need to learn how to use the calculator and to do these steps. So go back and redo all this, okay? And I'll see you next time for a little bit more yucked up talk about standard deviations. It gets a little bit messier, and I'll try to clarify that next time. Take you out with my good buddy Jeff Crompton and a little bit more from the album Standard Deviation. Enjoy. See ya. Bye-bye.